Nearly 50 years after it left Earth, a spacecraft the size of a small car has just handed scientists a discovery that is forcing them to rethink the very edge of our solar system. Not a new planet, not a new moon. Something stranger. A region of space right at the boundary where the sun's influence finally gives way to interstellar space that is somehow burning at tens of thousands of degrees in a place physicists spent decades assuming would be cold, calm, and quiet. Researchers have nicknamed it the Wall of Fire, and it may be the single most important discovery Voyager 1 has made since it first left our planet in 1977. Tonight, we're looking at what Voyager 1 actually found at the edge of the solar system, why the discovery upends decades of theoretical models, and why scientists are now calling it one of the most significant findings of the entire mission. To understand why this matters, you need to understand what Voyager 1 was doing out there in the first place. Launched from Kennedy Space Center on September 5th, 1977, the spacecraft's original mission was simple. Fly past Jupiter, fly past Saturn, send back photographs, and then quietly wind down somewhere in the outer solar system. NASA gave it 4 or 5 years. Instead, Voyager 1 kept going, using the gravity of each planet it passed to accelerate further outward, transmitting the entire time, decade after decade, long after anyone expected it to still be functioning. Nobody on the original engineering team was designing for a 50-year mission. Voyager 1 carries the electronics of the mid-1970s, computing power that would look laughably limited next to a modern digital watch. Its instruments were built to endure a handful of years in the environment near the outer planets, not 5 decades of continuous exposure to deep space radiation and the extreme cold of the void beyond the sun's warmth. And yet, here it is, still functioning, still transmitting, and about to deliver one of the most consequential findings of its entire career. In 2012, 35 years after launch, Voyager 1 reached the heliopause, the outer boundary of the vast magnetic bubble the sun creates around our entire solar system, formed by the constant outward pressure of the solar wind. Crossing that boundary made it the first human-made object in history to physically leave the solar system and enter true interstellar space. For years afterward, as Voyager 1 continued transmitting from beyond that boundary, its instruments kept sending back readings that didn't match what physicists had spent decades predicting. Before Voyager 1 actually reached the heliopause, the leading models describing that boundary predicted a smooth, gradual transition, like a river slowly blending into the sea. The solar wind would thin out gently, interstellar particles would gradually take over, and the whole process would unfold calmly across a wide, diffuse zone. What Voyager 1 actually measured as it crossed into this region was almost the opposite. Instead of a slow fade, its instruments recorded sudden, sharp shifts in particle density and magnetic field strength, almost like stepping over a physical threshold rather than drifting across a gradient. And buried inside those readings was the detail that genuinely stunned researchers: temperature. According to NASA's own analysis of the data, the charged particles in this boundary region reach staggering temperatures, somewhere between roughly 30,000 and 50,000 Kelvin, or approximately 54,000 to 90,000 degrees Fahrenheit. For context, that is hotter than the surface of most stars. Researchers quickly nicknamed the region the Wall of Fire, evoking the image of a boundary genuinely ablaze at the edge of everything we call home. It's important to be precise about what that temperature actually means, though, because it isn't fire in any conventional sense. There's no oxygen out there, no combustion, nothing burning in the way a flame burns on Earth. The heat comes entirely from the kinetic energy of charged particles moving at extraordinary speeds, colliding and interacting in an environment so sparse that despite the extreme temperature, Voyager 1 must pass through completely unharmed. The plasma out there is simply too thin for those superheated particles to transfer meaningful energy to the spacecraft itself. Think about how strange that combination actually is. A region of space simultaneously hotter than the surface of a star and nearly empty, so sparse that a spacecraft can pass directly through it without so much as a scorch mark. That contradiction is exactly why the discovery took researchers so long to properly interpret. Extreme temperature almost always implies extreme danger in our everyday experience, but out at the edge of the solar system, temperature and density have become almost completely decoupled from each other, producing an environment unlike anything found closer to home. It's a reminder that the physics governing deep space often has very little in common with the intuitions we build living inside a planetary atmosphere. So what's actually producing that heat? That question led researchers to the second half of this discovery, and it may be the more consequential one. Scientists had long assumed that the sun's magnetic field and the interstellar magnetic field beyond it were two entirely separate systems, cleanly divided at the heliopause, each behaving according to its own distinct rules. Voyager 1's data told a different story. As the spacecraft crossed the boundary, its magnetometer detected magnetic field lines from the sun's own heliosphere stretching outward, becoming compressed and beginning to interact directly with the magnetic field of interstellar space itself in a process physicists call magnetic reconnection. During reconnection, tangled magnetic field lines from two different systems snap, realign, and release enormous amounts of energy in the process, converting the kinetic motion of particles directly into heat. According to researchers studying the data, this reconnection process is very likely the primary engine behind the wall of fire, effectively explaining how a region so far from any star could end up burning hotter than anything nearby has any right to. That finding runs directly against one of the oldest assumptions in heliophysics. For decades, textbooks described the boundary between the sun's magnetic field and the galaxy's magnetic field as sharp and abrupt, almost like flipping a switch from one magnetic environment to a completely unrelated one. Instead, Voyager 1 found something closer to blending, an active zone where the two fields tangle together and trade energy back and forth rather than staying cleanly separated. Some researchers have gone as far as describing the alignment between the two fields as surprisingly similar in places, suggesting the boundary between our solar system and the rest of the galaxy may be far less rigid and far more porous than anyone had modeled before this data came in. That single finding rewrites something fairly fundamental about how our solar system relates to the rest of the galaxy. For decades, the heliopause was treated essentially as a wall, a firm, stable dividing line separating everything that belongs to our sun from everything that belongs to interstellar space. Voyager's data suggests it's closer to a dynamic, actively mixing interface, a boundary where the sun's magnetic influence doesn't simply stop, but tangles, reconnects, and exchanges energy directly with the galaxy beyond it. The heliopause isn't just where our solar system ends. It's a genuinely active physical process, still unfolding, still exchanging energy between two vastly different environments, and Voyager 1 is the only instrument in history to have measured it directly from the inside. This matters for reasons that reach far beyond academic curiosity. The heliosphere, the very same magnetic bubble responsible for the wall of fire, is also the shield that protects every planet in our solar system, including Earth, from the harshest cosmic radiation streaming in from distant exploded stars elsewhere in the galaxy. Understanding exactly how that shield behaves at its outer edge, how stable it is, how it interacts with the pressure of interstellar space pushing back against it, has real implications for understanding how well protected our entire solar system actually is over the incredibly long timescales that matter for planetary habitability, a boundary that behaves more dynamically, more energetically, and less predictably than earlier models assumed, is a boundary scientists need to understand far better than they currently do. Consider what that shield has actually been doing this entire time, largely without our full understanding of how it works. Every day, without anyone on Earth noticing, the heliosphere deflects a significant portion of the galaxy's most energetic radiation away from every planet inside it, including our own. That protection has been happening for as long as the solar system has existed, quietly enabling the kind of stable environment life on Earth eventually depended on. If the boundary responsible for that protection is more turbulent, more reactive to shifts in interstellar pressure, and more actively exchanging energy with the space beyond it than anyone previously modeled, then researchers studying the long-term stability of that shield now have a considerably more complicated picture to work from than they did before Voyager 1 sent back this data. What makes this discovery especially remarkable is the machine that produced it. Voyager 1 is currently powered by radioisotope thermoelectric generators that have been losing roughly 4 watts of output every single year since launch. A slow, irreversible decline with no possibility of repair from over 15 billion miles away. To conserve what power remains, NASA has been forced to shut down instrument after instrument over the mission's final years, including the cosmic ray subsystem in February 2025 and the low-energy charged particle subsystem in April 2026. Today, only the magnetometer and the plasma wave subsystem remain switched on, the very two instruments responsible for detecting the magnetic reconnection and particle behavior behind the wall of fire discovery in the first place. Every command sent to the spacecraft now takes close to 23.5 hours to arrive, with any response taking just as long to return, meaning engineers are troubleshooting a nearly 50-year-old machine in round trips measured in days, always one wrong instruction away from silence. And yet, despite running on a fraction of its original power, using instruments built with 1970s engineering, Voyager 1 is still producing data significant enough to reshape how physicists understand the edge of our entire solar system. In just a few months, on November 18th, 2026, it will cross a distance of exactly 1 light day from Earth, the point where even a signal traveling at the speed of light takes a full 24 hours to complete a one-way trip. No spacecraft in human history has ever transmitted usable science from that far away, and as it crosses that threshold, Voyager 1 will still be listening, still measuring the magnetic fields and particle behavior at the edge of everything we call home, continuing to answer questions nobody could have properly asked before an instrument was finally sitting out there to ask them directly. Nearly 5 decades after launch, built to last only 5 years, Voyager 1 just delivered a discovery that's rewriting the physics of our solar system's outer boundary, using less electrical power than the light above your kitchen stove. Whatever explanation scientists eventually settle on for how energetically active this boundary truly is, one thing is already certain. The edge of our solar system isn't the quiet, gradual fade into darkness anyone expected it to be. It is burning, reconnecting, and actively exchanging energy with the galaxy beyond it. And the only reason we know that at all is because one aging spacecraft refused to stop transmitting. No mission currently exists to send a second, better-equipped instrument back out to that same boundary, which means, for the foreseeable future, everything we know about this newly discovered wall of fire rests entirely on data gathered by a single machine, built decades before anyone understood what it would eventually find out there. If you want to be here for whatever Voyager 1 finds next, subscribe and turn on notifications, because this 50-year-old machine just delivered one of its biggest discoveries yet, and with its power still fading and only 2 instruments left running, nobody knows how many more signals like this one it has left to send before it finally goes quiet for good.